welcome everyone. Welcome, Serdar. And it's my very deep honor to have distinguished scientists to come to Hong Kong. And this is his first time to Hong Kong.
Shame.
I know, got to know Serdar for many years, and I got to know him really well when we had a chance to spend a whole week together in a boat floating around in the Mediterranean when he had a conference in Istanbul after the conference. So during that cruise, he played host to a few couples, including myself and my wife. And he's extremely generous in terms of spirit. I mean, the right kind of spirit. Means alcoholic drinks. So we have that in the morning, lunch, and dinner, and almost continuous for 7 days. And I said that he has to come to Hong Kong. He also said that they had the very best seafood. So, and I said that he has to come to Hong Kong. And I know that I cannot reciprocate in terms of the spirit, but I could certainly try to match it in terms of seafood. So we will have a day together tomorrow, and I will try to do my best.
The race is on.
The race is on. So let me give you a brief introduction to Serdar. I think he got his PhD from the University of Vienna in 1989. And he did a postdoc in the University of Stuttgart for 2 years. And then from 1992 to 1996, he spent 4 years with Alan Heeger in UC Santa Barbara, where he did the first study of electron transfer from the polymer to fluorine. And that is the beginning of the bulk heterojunction solar cells. And then he returned to Austria and became the chair of the physical chemistry in the Johannes Kepler universities at Linz. In 2000, he founded the Linz Institute for Organic Solar Cells. And so he's the force in organic electronics. And he also dabbled with politics. He got elected to the city council of Linz. So I didn't know exactly what you do there. Maybe you can tell us about
real estate.
Real estate. So he's a fellow of many societies, the Royal Society of Chemistry, the American Chemical Society, the Material Research Society, Austrian Physical Society, Austrian Chemical Society, and in 2014 he was elected the member of the Austrian Academy of Sciences. So he also won many awards and had quite a few honorary doctorates. I think the biggest award I think he won was the Austrian Science Prize. I think the prize money was up to 1.5 million euros.
Wittgenstein, yes.
So he is, of course, is very well known in the field of organic electronics. He published many papers, more than 500 scientific publications. And I don't know how anybody can publish that many papers. And they're very well cited, and he's one of the most well cited scientists in the world in the area of material science. So today he's going to talk about from organic to bioorganic semiconductors for solar energy conversions. Serdar?
Thank you very much, Ching. I'm greatly honored that I'm here, first of all, to finish the shameful situation that I've never been in Hong Kong. The second is that, of course, I'm surprisingly honored also that my other good colleague and honorable friend, Michael Gretzel is sitting also in the audience, so this is indeed a good get-together. Also, we will be next week in Guangzhou in the ICSM conference, all three. So today, I just wanted to take you on the general journey, because I was asked that this will be a colloquium, let's say, not in a very specified field, but since the specialists, world specialists, are sitting in the audience, it might be somehow, let's say, maybe boring to them, but I hope in the end I can contribute to some kind of nice discussions, which we may continue in the competitive seafood restaurant in the later on. So for the young people, of course, I have to indeed bring the very important slide. This is my famous slide, which I think this is the best description of why on Earth we should move to solar energy. It's not because of the cheap, because of the money, but it is there. It is there everywhere, and especially for the poor countries like in Africa, sub-Saharan Africa. And I gave a TED lecture, TED in Linz, it's called TEDx, about democracy and solar energy. And this actually led us to this famous, now famous, in 2011, we initiated in Linz, in Austria, an African network for solar energy. And this network is now over 2,500 scientists, African scientists, somehow interested in working in this kind of energy convergence. Every solar cell lecture, of course, should present this famous slide of NREL, which shall be updated every week, because indeed the perovskites are getting weekly records reported somehow. And you can see indeed, this is basically the Michael Gretzel's, let's say, work in the electrochemical dye-sensitized solar cells. This is our work with the organics. This is now getting really good, actually, also with Ted Sargent, and so these nanoparticles, I will come to this. But this here, these yellow lines over here, are the biggest sensation last couple of years. They are called perovskites. And let me start with the newest. These perovskites are indeed something which is very intriguing, because our honorable colleague David Mitzi was working his whole life, more or less scientifically, at IBM on this inorganic organic hybrid materials. And this is what he describes a perovskite system should basically characterize: either a van der Waals or an ionic or a covalent composite crystal of organic components with the inorganic. So this is a hybrid system. And indeed, these materials, which people use a lot these days, are based on this concept. This is methyl ammonium type of systems in lead iodide matrix. Of course, these elements are not, let's say, the preferential elements for environmentally friendly solar cells, but nevertheless, they became the GenePic these days. And the origin of this discovery went back for the solar cell, indeed, like Michael's work in titanium dioxide sensitization. But soon it turned out to be that you don't need this dye sensitization. These perovskite systems are themselves indeed a good semiconductor systems. And we indeed made also solar cells which can routinely give 13–14% solar cell, which is astonishingly high, just a sandwich structure between more or less here electron contact and here the hole contact. And these things indeed are perfectly fine, and as we always do, we did these things also to a very thin substrate. How thin can tin be? And you can put them on kind of, there's a video here, but I don't want to show you this. If somebody is interested, we can look at this. We made some kind of nice objects and planes. This was the paper last year in Nature Materials. We made some kind of these zeppelins. You can indeed fly them up and quite nicely. And the interesting part is, which is unexpected, these perovskites cast on a plastic stretched or pre-stretched system foil, you can indeed perfectly wrinkle them, perfectly deform them, and they still continue working on elastomers. So this was something which I didn't expect. I was thinking this inorganic matrix will more or less become very brittle and which will hinder that perovskites can become plastic solar cells. But this paper actually showed last year, and we extended this work more and more, you can indeed use plastic substrate technology on these materials. And since we don't need in these systems, as I showed you, titanium dioxide and sintering, etc., so this indeed perovskites enters these plastic solar cells. Another technology I was mentioning to you, especially now in the last couple of years, became very pivotal work of Ted Surgeon from Toronto. For example, you take the inorganic semiconductors, quantum dots, embed them in a plastic semiconductor matrix, and this also is, of course, deformable and can be shaped. And this today also is on the order of 10%. Solar cells are now getting there. And this is something which my good old friend Dieter Meissner was following, and he told me that this is actually a patent going back to 1968 from Philips. It's amazing that these people at that time made these kinds of solar cells, and these solar cells are based on not nanocrystals, but microcrystals of some kind of a grains, and if they are embedded in a plastic matrix, and if you polish this plastic foil back and forth side, you can contact each of these microcrystals, which are single crystal, perfectly to a nice efficient solar cells. Those days, of course, people were using cadmium selenides, cadmium tellurides, all kinds of things. But we are now using, of course, more this copper indium sulfide or copper zinc tin sulfide systems. Dieter actually initiated a company called Crystal Sol in Vienna and Tallinn. They are really working on this heavily to make a real plastic formable solar cells. This is, let's say, our baby. As many of you know, this Konarka Incorporation basically made this kind of productions. Unfortunately, they filed Chapter 7 on 2008, 2009. So this was indeed unfortunate. This young man here, on the side of the other young man, you may recognize, his name is Christoph Prabetz. He was my first assistant when I came to Linz. He himself is now a big professor in Erlangen University in Germany. He was many years the CTO of Konarka Corporation. So this semiconducting dyes is indeed a very interesting approach because you can make them or use them as inks, and that opens up several things, of course. But for me, scientific, especially chemists maybe sitting in the audience, it's most important is that you can manipulate the electronic structure by manipulating the chemical structure. And that flexibility of the organic chemistry is, of course, amazing. You cannot do this with silicon. Silicon has indeed 1.15 electron volt band gap, and this is it. There is nothing much to do about it. But here you can change the band gap over electron volts. It has implications for example, OLEDs, as we see, for example, here in this nice Lumiotech in Yonezawa. They have all kinds of colors, indeed displays, etc. And we know the Samsung Galaxy, and Ching is, of course, sitting here, is very well the godfather, if I may say so, of this technology. And this is something which is great because you can manipulate the color by chemical manipulation of the structure. For example, we also took these OLEDs on the plastic, and this is now PLEDs, so polymer light-emitting diodes. And we did the same trick at that time. Matthew White, my student, who is now my postdoc, who is now a professor in Vermont, and he basically made this also crunchable, stretchable kind of LEDs. And it's amazing, you know, under stress, under elongation, they still work. I mean, they still emit light, and there is some kind of ruggedness in there which was unexpected also for me. By the way, this is for the students an interesting book which finally we wrote a couple of years ago, came out with Alan Heeger and myself. This is for student teaching book actually on semiconducting polymers. So a little history telling, since the people are sitting here, of course, and I would I would be honored to tell this story. I tell this story also in your absence, Ching. So I'm not the inventor of organic solar cells at all. I mean, this honor, if anyone indeed deserves with this famous tongue cell, these are the dry, evaporated, thin film single solar cells. And Ching told me that actually this 96 paper is deceiving. And indeed, I went back and look, the patent. And he is right. 8 years before, the first patent came on solar cells and told me he discovered the LEDs by investigating solar cells. So in that sense, there is maybe coming home in one day, going back to solar cells. So students read patents. I mean, this is something really, really interesting. And how this tongue cell works, it's very simple. In one point, there's an absorber. This, let's say, is the donor. And if you excite, there is some kind of exciton state, and this exciton have to be dissociated at the interface of an acceptor, and you collect the charges. But you see immediately here, which is the shortcoming, the exciton diffusion length to the acceptor interface is only order of 10, 15, maximum 20 nanometers. So these things have to be, these films have to be really thin on the thickness range of exciton diffusion length, which is tough. I mean, to structure something in 10 nanometer scale is tough even for the UV lithography. So our contribution was this, let's say, bulk heterojunction, which is possible if you have something soluble, processable. In that sense, polymers, of course, became very much handy. If you mix these components, not in bilayer, but in one mixed single layer, at that time we used these fullerenes, because it was new in 1990s, it was very fashionable, and this was the paper which Ching was mentioning, 92. And in that sense, there is an electron transfer, and this is the P conductor, this is the N conductor, and I will show you in a minute how it should probably work. Somebody maybe sitting on the audience never seen a fullerene. This is a real picture of fullerene. It's given to me by Thilo Glatzel, actually, from Uni Basel. In this high-resolution AFM, you can even see 5-fold and 6-fold facets of fullerene in a real image. It's not a cartoon. So this is something nice. So, talking about patents, we had also a patent. This is August 92. And in this patent, actually, we describe the definition of a bulk heterojunction is a heterojunction between the polymers and acceptor materials formed in situ by controlled segregation during solidification from a solution containing both the donor and acceptor moieties. So basically, you mix these two solutions and cast from one solution, one single layer, and hope the best that it really phase separates to a nice system. So this was actually the definition of heterojunction. I show this because indeed this claim was patented 2 times. It is 5 years later and 15 years later. And there's interesting, I mean, sometimes I have the feeling the patent offices also don't read patents, I mean, somehow. So this is this solar cell. You can also make it shrinkable. You can make this very thin. This is Martin Kaltenbrunner and Matthew White. Again, this couple, you see, it was in 2012. So what is important on this ultra-thin lightweight? And many people were asking me about the advantages of organic solar cells. Many years we were talking about cheap solar cells, but that doesn't work because silicon is today cheaper than anything you can have. So in that sense, and I believe the real advantage is this form factor first, and second is this value here. And as we published this first time, it was more or less adventurous gag, which I wanted to have, but you see watt per gram here. And normally, all solar cell specialists publish watt per square centimeter. This is the efficiency of the solar cell. Why on earth somebody would publish produce watt per gram? And in that sense, of course, you see these plastic solar cells are orders of magnitude higher than the silicon solar cells. And after this paper was published, I received phone calls from ESA, NASA, US Air Force, everybody was calling, because for space applications, the most important parameter is the weight. This costs millions of euros to bring kilograms up to the outer space. So this is something which is apparently important, and it could be now at our discussions of lunch, indeed, it can be an important issue in future. Textiles is another issue, of course, especially these functional textiles, power-producing textiles, sensor textiles. Imagine this is not a photoactive, but some kind of chemoactive material. You can have chemical sensor diodes, etc. in here. This is one of the last stories we had with Arvid Hübler. Arvid Hübler in Chemnitz is neither a chemist nor a physicist, but he is a professor for printing. Interesting, in Germany you have professor for printing. It's a historical, of course, tradition. Indeed, this printing was discovered by Gutenberg in Germany, and Germany has indeed hundreds of years tradition. And we were discussing what kind of substrate we should use all the time. Is it polyethylene terephthalate or polystyrene or something? And he was telling me all the time, he said, why don't we use paper? He said, we have experience in paper printing at least hundreds of years, and we know paper around thousands of years. So this is something which is biodegradable, fantastic. I will come to this point. So we made this project, European project, and indeed showed with some tricks, you need, of course, some modifications. You can make a real roll-to-roll paper printing machine, and on paper substrate, you can get around 3–4% solar cell without, let's say, much difficulty. So just repeat the concepts. Indeed, light absorption is important, of course. Our systems absorb light too much in the blue. We have to shift the absorption to the red. And this can be done nicely, as I told you in the beginning, by making this chemical structure manipulation on the backbone. You can get low band gap materials, change the band gap, and that's indeed something which was so efficient and so successful in the last 10 years, I would say. And today the world records are on the order of 10–12% now, and mostly these kinds of polymers coming from Mario Leclerc's or the Looping U labs, and there are now many companies, of course, all around the world. And in China also many groups are doing this, as you can see here. And this is something, a strategy which is working, shift the gap to the infrared. But of course, if you do it, you make a hole in the visible. In normal cases, we don't have a band absorption here. So what should we do there? And at that time, we were thinking about this, especially with Gion Calzaferi. He's now retired in Bern, is a very good colleague of mine. And he was suggesting these kinds of energy transfer cascades. And we used this, his help, and Robert Kepler, my student, he basically made these kinds of nanoparticle cascades. This is an antenna logic. So you absorb the light and energy transfer the light by first-order energy transfer and get on the end to the reaction center, which is the electron transfer couple, here zinc, ferrocyanine, and fullerene. So the second approach is you can make two solar cells. One is absorbing in the blue, one is absorbing in the red. Put them together, and if the current matches, then it's a very good serial connection, and you can get nice tandem solar cells. But it's difficult, of course, technologically, because you are increasing the number of layers you are casting, and that's, of course, not so easy to do, but it works. And the open circuit voltage is up to now generally accepted that this is between the quasi-Fermi level of the donor, which is more or less close to the HOMO level, highest molecular orbital, occupied molecular orbital, and the LUMO, the lowest unoccupied molecular orbital of the acceptor. So that distance is more or less limiting the quasi-Fermi level splitting. And we checked it experimentally by manipulating these HOMO-LUMO levels by different substances. Indeed, this is C60s, different C60s, for example, the first reduction potential, which is the LUMO level, and the open circuit voltage go nicely linearly together. The same thing also for the highest occupied first oxidation level of the polymer donor. And all these points are different materials, but they all line up beautifully. So that concept seems to be also working. The second, the last and the third one is this structure nanomorphology relationship. If we look to the nanostructure, and there is one picture missing here somehow, this, of course, is a mixture which demixes itself by spontaneous phase segregation, which leads to an enormously disordered structure. And if we cartoonize this kind of picture, we have wild and disordered mixture of nanoparticles of donors embedded into the nanoparticles of acceptors. And that doesn't seem to be a very, very nice physical system. And indeed, if you just change the solvent, for example, absorption doesn't change, but the solar cell efficiency can be increased by manifolds. So how this comes, and this is basically the theory of another Nobel Prize fellow, and then this is indeed the transport in disordered media. And indeed, if you have order in crystalline or amorphous or polycrystalline, there is a difference in charge transport properties of the system. And actually, Mott and Anderson get the Nobel Prize for this. If you have some kind of a system which has heavy disorder, the energy states which are below some kind of a mobility edge are localized states. So the charge carrier can only hop between the states. Only above this mobility edge, you have some kind of, let's say, metallic or some kind of a ballistic transport. So this ends up, I will just skip these details, but this ends up what we call Poole-Frankel type of field-activated and temperature-activated transport, which acts exactly opposite. Normally, in a good semiconductor, in a metal, if you cool the system down, the system gets more conductive and more mobility. In our systems, if you heat them up, the system, of course, gets exponentially better conducting and mobility. So this is something which is still coming from the disorder. And if you have such a huge disorder like we have, by the way, we can check these kinds of mobilities very nicely with this diode configuration or transistor configuration. In the diode configuration, I recommend very much the SELIF systems. This is called charge extraction by linear increase of voltage. So it's abbreviated as SELIF. And this SELIF is indeed a diode configuration, and this is a very good method to do these kinds of mobility experiments. And indeed, you can see this is very much activated Arrhenius type of behavior. And there are very funny systems, funny effects like this systems, what we have Meyer-Neldel points. So these are details, but if somebody has questions, I can come back. So what do we need? We need an order in this interpenetrate network. And in one point, it's this picture I was showing now, good 20 years now, and somebody did it. And somebody did this, and this somebody is Shunji Aramaki in Mitsubishi Kazei in Japan. And this fellow actually made these kinds of precursors of benzoporphyrins, and if you heat them up, they basically turn into the real benzoporphyrin, and they create these nano needles coming out of the surface beautifully, and you can fill the rest with the acceptor. So that looks very much like this cartoon I was showing. And to my opinion and to my knowledge, that this is still industrially very close and getting in the order of 10% solar cell. There are other things for chemists. For example, one can use indeed D-block copolymers and orient them by self-organization strategies. There are several works around there. I always cite this work, my good friend Sam Janicke. I mean, it's indeed, he's now University of Washington, retiring. It's beautiful, these micelles. Of course, we need that in cylinders, so we have some kind of coaxial cables. Another idea is to hook the donor and acceptor together to one molecule, and then in that sense, we don't have percolation type of problems, disorderless. So indeed, this kind of what we call double cable polymers were synthesized in a European project in our institute 20 years ago around. The problem is that these materials with thiophane, with fullerene, of course, soon reach the solubility limit. You cannot make these things soluble practically in many ways. So this is a bad news, but this is possible. So let me take you now to a small journey. How much time I have, by the way? 1 hour, something together, or less? All right. So I will really take you to this journey now. Indeed, the biodegradable story. So how I came to this bio, and I said I was educated as a physicist, and since 1996, as Jing was saying, I'm basically chairing the Institute of Physical Chemistry. So I made already metamorphosis into a chemistry professor. And I say to all my friends and colleagues in the, let's say, next maybe couple of decades, if God gives me the time, I will move more and more to biology. So this is now, I will tell you to this, take you to this journey. So how we came there is this famous question of biodegradation. Why? Because the electronics is getting really from consumer electronics to consumable electronics. And this statement, very famous statement, is from this legendary chairman of Sony Corporation, Akito Morita. He said, indeed, correctly, we have today billions of phones we are doing and we are more or less wasting. And if you look to the plastic waste we are producing, even without the plastic electronics and plastic solar cells, which is really, really very, very bad. I mean, these are in Pacific. Maybe you have similar problems here in Hong Kong, but definitely in Hawaii or other places, we have these big gyres. And you see maybe that gyre also affects somehow Hong Kong. And this is bad. I mean, we should not be proud of it. This polyolefin production in the world and plastic usage in the world indeed is making the planet not a good place. And this, we cannot use this planet up in that way. I mean, I don't like this strategy at all. So, now in 2006, I said to my team, I want to have organic, biodegradable semiconductors, conductors, insulators, whatever, electronics. So they went out and they start searching and they found, I mean, for example, beta-carotene is a perfect P-type semiconductor. You can eat it. Of course, caffeine, sugar, these are all nice insulators. And so Mihai Irimia Vladu, he is now professor in Graz, Johanneum, and he actually made a religion out of it. He indeed went up and made very beautiful materials. You see, for example, this is a beta-carotene transistor made with glucose. So look at the numbers. Of course, these are academic numbers, but it works. So indeed, you can have some kind of a organic or bioorganic semiconductor system. So, by the way, glucose in the caffeine makes the transistor better. And then he went that far that he was making these transistors and he was eating them after measurement. So it became the title picture of Advanced Functional Materials with Edible Electronics. That was our paper at that time. And we had all kinds of CNN, Wall Street Journal, everything, all the people, ARD and CDF in our institute. People didn't want to see an electronic. They wanted to see somebody eating an electronic, so they were only interested on that. So on that journey, we discovered actually this material. And this material is actually the oldest material known to chemistry. It's called indigo. It comes very close here from indigo. Indigofera, this is from India, of course, as you can see. And this is the color of pharaohs. It's mentioned in the Old Testament and dozens of times. And by the way, look at the price here. This is $3 per kilogram you can buy today. This is this molecule. So this molecule per se doesn't look actually as a semiconductor to me. But through this hydrogen bonding here, it gets some kind of internal tautomerization type of delocalization, apparently. And these hydrogen bonds will become very important. And this material is indeed the basis of German chemistry. As we know, industrial chemistry was developed in Germany, and especially on the last 1800, end of 1800s, beginning of 1900s. And indigo actually coming from Portuguese word, which is called anil for indigo. And as many of you know, aniline is just produced by heating indigo. And aniline is the basis of the entire German chemistry companies like Agfa, BASF, or at that time IG Chemie. So it's indeed something which is very important historically, just for this historic excursion. So we took this material and made field effect transistors and solar cells and diodes and everything. So what comes out? The first thing is that the material, by the way, it became also an indigo electron, another title, Picture of Advanced Materials. It's an ambipolar material, ambipolar transistor. Electron and hole mobility are more or less 10 to the minus 1, 10 to the minus 2. So it's quite good material. But there is always a better one, and this is this one, di-bromo indigo. For a chemist, it's a simple bromo substitution. But in antique times, it made a big difference because this here is only coming from the seashells, and it was the most expensive dye. Only imperators, Roman imperators, had this purple, and it's called royal purple because of that. It's very expensive at that time. For today's chemist, it's of course not very. So, and if you look to this material, it's amazing. I mean, it's perfect ambipolar, more or less negligible hysteresis. You get 0.1 order of magnitude, beautiful mobilities. And this material is stable. And if I say this, I mean it. And we know that organic electronics had always suffered because of the stability issues, especially in many kind of photostability issues. We have indeed less lifetime, let's say, compared to inorganic silicon with an oxide on it. However, these materials are really stable. You process them in air, you don't need any kind of encapsulation, and they work. And if you want to see the same color of indigo, if you visit Egypt, you would see thousands of years indigo paintings, still the color is there. So temperature stability is amazing. I mean, this quinacridone is a relative of indigo. I call it hydrogen bonded pentasane. So this goes up to 600 degrees stable. So this makes a big difference, of course, now industrially. Why it's so stable? Our assumption is that these hydrogen bonds play a big role in this kind of semiconductors, and therefore we gave the name to this family hydrogen bonded semiconductors, because I believe this is the general umbrella we have to look. And indeed, that makes stable materials. We know from cellulose, for example, even the synthetic Kevlar fibers are based on their hydrogen bond, and it's very stable material. People use this material for bulletproof clothes and helmets. So, this is, for example, quinacridone. This is my champion material. This is pentasane. As you see, very similar, just the hydrogen bonds are, let's say, therefore it's indigoid family, but indigoids maybe you don't use, we call hydrogen bonded semiconductors. And it's a very nice, basically higher dielectric constant. We can make diodes out of it, and you can get nice photo effects, solar cells, even from a single layer of quinacridone, you can get nice photo effect. But this is the most important thing. Look at the transistors made from pentasane, made from quinacridone. Identical conditions, identical setup, and look at the stability. Indeed, tetrasanes and pentasanes, they are really dying on a matter of, let's say, a couple of days. And the quinacridones, epidendrinions, are very, very stable. These are in air without any protection, constant operation. So it's so stable that you can take this epidendrinion, for example, put it into water. Why would you put an organic field effect transistor into water? Nobody will do electronics underwater, but it's important for biological. Because every biosensor, every bioelectronics you want to do has to operate underwater. And this, up to now, to my knowledge, nobody has established in any kind of organic semiconductors, except this that we found now, these hydrogen bonded semiconductors are indeed insoluble and operational under pH 3 all the way to megaohm, pH 7, pH 14. It's fantastic. So why it's so important? For example, we can surface functionalize these materials, and this opened up a new field, basically. We have several theses finished now. Papers are coming out. You can put all kinds of this kind of biotin, avidin type of plays. You can hook biosystems onto the organic semiconductor, and indeed, fantastically working. So I will come back in a minute to this a little bit, but this material are really making beautiful, we call them pigments, which are making the color actually in a more solid state effects. So, and there was a nice idea of Michael Sitnik. He finished his PhD, is now in Erlangen too, and basically he made a nice nano solutions, nanocrystals. These are organic nanocrystal suspensions of these materials. So this is for inkjet printing, etc. Quite important how to make these things processable. And we can make all kinds of nanostructures. You can see here. That paper really great, get a real attention the last couple of years now. So conclusion, indeed, stability and even underwater stability is possible. And that comes now to the biological applications in a great deal. So, but let me take you the last journey, which really fascinates me these days, is this solar energy conversion to chemical energy. And of course, it seems like a déjà vu to my dear friend Michael Grätzl, because if I remember correctly, this was also the original idea how to make chemical energy out of solar energy. That was the holy grail of all this artificial synthetic photosynthesis type of systems. Why do we need that? Indeed, all renewable energies have this problem. If you convert the energy from wind or solar, you might need it later. So you need shift this energy in time. That means you have to store this energy. And if you have the same site, you want to store this energy, you might get away with battery systems or battery banks, but I will show you their shortcoming too. But if you want to shift, not only in time, but also in space, that means in North Sea in Germany, we have an enormous wind production, but we need the energy in the South Germany. So they are thinking now around 50 billion euro investment to have a north-south energy, high energy transfer truss. So that's a problem. If you create the energy in Sahara, there's enough solar energy there, but we need it in the middle of the Europe. How you get the energy there? So the conclusio from this diagram, I call the space-time problem, is a transportable field. If we create a transportable field from renewable energies, that will indeed solve this dilemma once for all. So, look at the batteries. I mean, some people are, of course, working in batteries, and I'm very much in favor of a good work in batteries. Tesla makes a good job on that, but we need even more efficient batteries. However, look at the numbers. Best batteries we have today are on the order of, let's say, 50, 60 watt hours per kilogram. And a simple 1 liter gasoline, it's on the order of 20 kilowatt hours per kilogram. So if you just look to these numbers, it's immediately clear that even if the battery technology would get, let's say, a factor of 5 better, we are still order of magnitude off from the liquid fuel which we use today. And that technology is a very important story. By the way, for students, I always advise to sit down and calculate what is the power needed for a car if you go to the gasoline station and pump up your car with fuel. And if it takes longer than 2-3 minutes, you will be very upset and angry because the machine is not working in high efficiency. You are transferring 40-50 liters of gasoline in 3 minutes maximum from the gasoline station to your car. If you calculate the transfer power of it, it turns out to be megawatts, tens of megawatts. So if you want to transfer the same amount of energy electrically, you need supercon cables or cables with the average of mega ampere running through the system. So there is a problem here in general. So I want just to show it, but battery research is, of course, a very beautiful field of work. So the second one is the capacity number. If you look here, this is the actual, and it's now much worse, June 2009, E.ON Transpower Netz in Germany. This is the wind power coming in. And look at these numbers. Ladies and gentlemen, look at these numbers. These are 8,000, 6,000 megawatts. This is 6 or 8 gigawatts. These are at least 4 to 5 nuclear power plants on the size of Fukushima turning on and off within minutes. This is unbearable fluctuation. This is impossible to buffer. Look at this integral of this peak here. If you want to power up this integral into batteries, you end up in 80 million kilowatt hours, and this is the world production of batteries around. This is amazing. I mean, this is something which we have to really think about this. If we want to buffer the wind energy of Germany for a big scale, we need a different power storage system. So the idea is very simple, of course. CO2, renewable energies, and water create an artificial fuel. The idea is not new. Somebody came to the same conclusion 3.5 billion years ago. You cannot even patent it. So you can indeed get the CO2 back electrochemically or photochemically. Maybe detailed patents are possible. But this is the first semester C1 chemistry. You can see here methanol actually is what George Olah likes very much. But it 8 electron reduction, final station is the methane. This is the gas which Russian basically pipelines bring to Europe. So can we do that? Yes, we can. You can take carbon dioxide and water, pump in the renewable energy, and get the methane and oxygen back, for example, in an inverse fuel cell type of operation. And it has to be, of course, this energy coming in, a renewable energy, to make sense. Otherwise, you cannot use this coal-powered energy to make CO2 recycling. That would be, of course, complete nonsense. So this is the basic nice book in 2006 from George Olah, another Nobel Prize colleague in the University of Southern California. George likes methanol very much, but he put also methane to the power. So we went down and then created this small company, which is Solar Fuel in 2006. And basically they went 2009 to Germany and then changed the name to A2Gas. And basically there's a very nice collaboration with Audi. Audi, they built this nice plant. These are power plant builders. The spin-off now of Linz we are now having now in Stuttgart. And basically there's a huge system which is directly coupled to a biogas system, biogas plant, and taking the dirty biogas and upgrading it with the CO2 recycling with the renewable energy coming from the wind. Therefore, they changed the name because solar fuel, they should have done in Germany wind fuel. In that sense, they generalized this to A2 gas, electricity to gas. And these are real megawatt plant systems. And Audi, and I think that's a very good ansatz, is that if you take a gasoline which is created by CO2 recycling and renewable energies, you are actually consuming as much, you are emitting as much CO2 as you have put in the first hand. So it's a CO2 neutral cycle in the vehicle operation. And it should have gotten the same tax advantages, for example, of a Tesla, because this is the same story. I don't know if they will be successful, but I really support the idea. Scientifically, there's a vast field here. It comes from organometallic chemistry, all these beautiful catalysts you can find in the literature. And now coming back to our original idea. And indeed, it's very interesting. I always said photovoltaic solar cells using electrochemistry, is photovoltaic operation like Michael Grätzel's solar cells. I mean, we had many discussions. The electrochemistry, it's good or bad, but now we are coming back to electrochemistry. So these solar cells are electrochemical solar cells in the real operational sense of these titanium-based solar cells. But here, for example, donor acceptor systems, if there's an electron transfer, you can take the electron by reduction. And you can take the hole by chemical oxidation. There are no wires here. They're just chemical cycles which are pumping the entire photo system. So is it possible? This is a little bit busy diagram, but I will just go through this. For example, this is a polymer electrode, imagine. It excites, like I showed you before in the tongue cell in the cartoon. Electron transfers to LUMO, but it doesn't go anywhere in the circuit. It just goes to the electrochemical catalyst. And this catalyst takes up the electron and makes the CO2 reduction. And the whole, for example, we can take comfortably out to the outer circuit. The same thing for titanium dioxide, of course. Michael is doing for the opposite operation. The electron is doing the job of reducing the CO2, for example. Is it possible? Yes, it is. For example, this thiophane, polythiophane, you can transfer the electron, something like a predynium. These are homogeneous catalysts swimming in the solution, and CO2 is to methanol possible, for example. Bocarsley also made, but we have some problems with the Bocarsley catalyst. We made better ones. And this hole is taking out the contact. Is it possible? Yes, you can see if you put CO2, for example, electrochemical current is very much more increased. So this is now more getting into the electrochemistry in the cells, electrochemical solar cells. We also made these kinds of conjugated semiconductors with this catalyst on that. Rhenium, by the way, we always use, because rhenium was first suggested by Jean-Marie Lane as one of the most efficient catalysts of CO2 reduction. And we use, this is the Jean-Marie Lane catalyst. We use all kinds of modifications of this, and they work. I mean, Engelbert made his PhD on this. He's now assistant professor in Innsbruck. And I call this, or we dubbed this generally many, many years, 1992, many years ago, I said these things, this third generation of conjugated polymers, because first generation was the pure ones and the other ones were soluble ones. And the third generation are the so-called functional ones. And this function now, for example, can be an electrocatalytic function. And we synthesize these materials, electropolymerize these materials, and indeed they are now heterogeneous catalysts. The catalyst is hanging on the electrode and not moving in the solution phase. So this just came out, but the work has been going on for a long time because it's not so easy to synthesize these molecules. And we went even one step further. I told you before that some organic semiconductors we have are biological environment stable underwater, and the idea was, why don't we put an entire reaction center, biological, photosynthetic entire reaction center onto the organic semiconductor? Why not? And it's possible, especially with this hydrogen-bonded semiconductors, we can do that. And Eric's paper basically showed that together with the Barry group, who put the biological system on that. And indeed, for example, this is a transistor configuration, but what we are doing is we're just measuring the photoconductivity, and you can see indeed bioelectrical signal from this reaction center by light and detecting it electrically. And to the best of my knowledge also, this is one of the very few direct observations of this bioactivity of the system using organic semiconductors. Another step is, of course, using biocatalyst itself, because biology has done a great job over the billions of years, and it was a brutal institute. You know, if the students fail, you know, they were killed. So this is a heavy motivation in nature to make the best evolution, and there are indeed enzymes, what we call dehydrogenase enzymes, taking from the CO2 all the way to methanol, and we use them, and we immobilize this, for example, and now you see why I'm saying that I'm getting more and more biological these days, and indeed you can make this. My good friend Michele Aresta in Bari, I mean, they are really good on this. They showed me, I mean, he showed us this, making these beads. These beads are alginate beads, embedded, immobilized enzymes in there, and they work. You can bubble CO2 through that, and indeed you can get from the CO2 all the way to methanol. But there is a shortcoming. And this is this issue here. Every time you make this transition, the enzyme needs some food. And the food is this substrate, they call this NADH. It has always to be oxidized back to NAD plus to make the machine running. And that's bad news. Because NADH is not only expensive, but also unstable, etc. It works perfectly. Under normal atmosphere, normal temperatures, this is one of the best things in biocatalysis. It works under so mild conditions. And NADH can be recycled, so we said, okay, can we make a semiconducting polymer electrode which recycles NADH? Yes, it's possible. This was the very attentive paper also together with Günther. He made actually this rhodium compounds. Kerstin, our joint students, was in JAX. However, the idea is to get rid of this NADH altogether. This NADH, what does it do? It brings an hydrogen equivalent to the system. So either you bubble hydrogen into the system, which is one other way, or hydrogen is just the equivalent of electrons. So I said to my people, and especially this Stefanie Schlager's PhD thesis, I said, why don't we give to the enzymes direct electrons? Electroshock them. They are not living, they are immobilized, and they indeed took up the electrons. And this was surprising. I didn't expect it, this I have to admit. Indeed, you can run all this cycle by purely electro-injection to the enzymes. And it looks actually very ugly like this. You can take some kind of an electrode, put it in the alginate matrix with all the enzymes in there, and pump electrons into the system. For example, we made also butanol. Butanol is a very good diesel substitute. And you can indeed see very nicely butanol is produced. So the enzymes are active, they are working. And there is no NADH in the system. There is no substrate. We are just pumping with electrons. So I believe this could be a very interesting avenue in very near future. I know many people are now jumping into this story. So finally, our institute, indeed, we are moving more now into the CO2 recycling with biosystems and also organic electronics into bioorganic electronics. Indeed, maybe in the last section of my scientific life, maybe I will be a biologist. Maybe my next professor, she will be a biology professor somewhere. We will see. So I thank, of course, many people, just a cross-section of many people contributed to the work I reported here. FAF, especially within this Wittgenstein Prize mentioned by Qing, it's indeed a great, great relief. So in one point, I thank all my colleagues. And of course, this is the conference which Qing was mentioning. We made this conference, Solar Energy for World Peace. And we wanted to repeat it. I mean, especially Walter Kohn was very much initiating member of this committee, but he passed, as you know, a couple of months ago. So I would really repeat this conference one day, somewhere, and I would definitely come back. Both Michael and both Qing were there, and it's indeed something which could be important for future. So thank you for your attention.
I wanted to comment on the indigo. It's a very nice idea. I heard you talk about this several years ago in Sardinia, a conference. And the issue with indigo is, though, that makes it stable, the hydrogen bonding is also deactivating the excited states in very fast radiationless process. And so the hydrogen bonding is a blessing, but it's a mixed blessing. It's used also in the red car pigments, the dipyroluperol. This is a strongly hydrogen bonded system. You would think, oh wow, that's a good semiconducting system too, but it has no carrier lifetime. So for photo, it's not an option, unfortunately.
This for indigo, it's correct, but the point is that we have also somehow went into the chemistry of indigo, and there was exactly the same discussions. The hydrogen bonds indeed deactivates the excited state. And at one level, there was this idea. Now I have to show this probably, yes. Especially from Gundula Foss. Gundi Foss was a retired chemist, professor from Bayreuth. She actually took these kinds of what we call T-Bock group into the system and more or less turned off the hydrogen bond. And this basically made the system even, this is like here, makes even soluble in organic solvents, which was not before. Indigo is very difficult to dissolve, but this T-Bock trick, this I didn't mention now, but there is a paper in ChemCom just 1 year prior to this, 2013, with Gundi Foss and Eric Glowatsky, Eric as first author. And that trick of Gundi worked really well. So you can indeed have a chemical tool to basically turn on and off the hydrogen bond. And the interesting part here is if you take this, make a nice film cast and heat it up, for example, around 150 degrees, then this T-Bock group leaves and it comes back to the hydrogen bonded state. So this is some kind of a transient chemistry, which has advantages to make these kinds of nanoparticles. This is how you make these nanoparticles using this T-Bock trick, the hot injection. But you are right, if the indigo is hydrogen bonded, this is bad news. But there is a chemistry, and again, my chemist colleagues are highly appreciated. They have tricks how to turn on and off this hydrogen bond. So maybe, let's say, it's a problem, but maybe we can handle it in chemistry. I hope.
Interesting, Michael, this hydrogen bonding. I may have something to add to it. The discovery of organic laminating diol in Kodak was based on a compound that has hydrogen bonding. And I will disclose it for the first time in Guangzhou next week. And the way to get rid of the hydrogen bonding, which I did some 40 years ago, was to cool it in liquid nitrogen. And so you freeze the, I actually use the same compound, the indigo kind of compound, for light emissions. And actually the compound is in your slide, I was very surprised. And it actually worked. I mean, you can get a very high efficiencies, almost 30 times higher compared to room temperature. And it's reasonably stable, light emissions. So you're right about the deactivation by hydrogen bonding of the excited states. And there's another second example that also related to organic laminating diols. And also the compound is in your slide, is the quinagones. And it is very insoluble material.
This is the one.
Right. And also, but if you can isolate this material and put it as a dopant in a host, and it's very efficient light emitters emitting in the green, but almost has zero stability, lifetime. And you have to get rid of that hydrogen. And the way we did it is to put a methyl group in it.
Okay, methylation.
All of a sudden, the material would be stable. And it's still being used in some way. So this hydrogen bonding is the benefit in some way, but it's a curse in another. But there's a way of getting, making use of it, and also a way of trying to get rid of it. So just something to add to your questions.
Maybe a little bit related. In a later slide, you showed this pyridinium system. So I wondered then if you require the hydrogen to be part of the chemical reaction, or again whether you could have, it's more of a redox issue, and if you methylate it, you'll fix it as positive charge. Will that switch off the whole reduction process?
Yeah, that's actually a very detailed question. It will take very longer, much longer to explain, or maybe even not to explain in detail. The preadenium radical was suggested by Bocarsley and his group for being a very efficient methanol catalyst. And let's say, to be very carefully formulated, people had massive problems to repeat this experiment. And there was great dispute in the literature. So we basically showed that you can make praseodymium type of many other related compounds which work actually better. This was in that paper here.
Even bipyridine, because the radicals are really quite well established in our system, and maybe that would stabilize it a little bit. But I don't know the detail within your cell. I worried in a single ring it's maybe a little bit too, I don't know, the energy gap seems more.
So the systematic study showed that this indeed works. I mean, Bocarsley was elementarily right. But the efficiency of that catalyst to take up the electron and make this 6 electron, 6 hydrogen story with CO2 is actually more or less limited. You need many, many of these pyridinium ions, or in that sense, if pyridinium is radicalized, it's a neutral radical actually. You need many of them to work together to get this done. So in that sense, there is a problem here. And probably this knocks down the efficiency, and this was the big dispute in literature. Many people didn't see the product as claimed in the papers. We investigated this Engelbert PhD thesis with many related compounds. Indeed, it works, but there are much better ones, let's say this way, which has to do also with number of the protons. If this proton here is in the positively charged state, proton is well bound. But if you radicalize and get rid of the positive charge, this NH bond becomes very loose. So it can indeed somehow cooperate, giving also the protons necessary, probably, to get into the synthesis of methanol. But indeed, I have to admit, there is no clear picture how all these things work and how all these things should look like in the end of the day. My ansatz is that we indeed went away from this homogeneous, but we went to the inhomogeneous catalyst, so that at least I know that these catalysts are sitting on the electrode in a kind of a spongy structure, and they are not swimming in the solution like in the homogeneous catalyst, which made life much easier, of course, especially for the concentration of catalysts. Otherwise, everything is swimming everywhere. It's not so easy electrochemically to address the system.
I just thought maybe a bipyridal system, maybe if you have to have NH, you have it on one end, and maybe an NMe on the other, and that type of species maybe.
Yeah, we tested Bioorganic, of course. Bioorganic is the first test,
yeah.
But Bioorganic is too low. So we have to lift it up.
So you need more energy gap, you mean?
You need some kind of tilted piperidine.
One more comment, since the selenium.
Yes.
We got also very excited about Linz. It's Linz.
1984 or whatever the paper.
Yeah, but the truth of the matter is it has a very low turnover number. I mean, we thought they had done something wrong. After 1,000 turnovers, the thing is dead. It should have 100 million turnovers to turn over, say, for 20 years in sunshine. And so nature, the leaf can resynthesize every day. so yeah, you got something that, I mean, 1,000 turnover looks impressive, but it's gone very quickly. My student and I were puzzled. We were looking at what had happened until we found out that's actually, that catalyst is very unstable. So we still, with a homogeneous catalyst or heterogeneous catalyst, if you go to good old copper, Professor Horry's work, that's catalytic. So a nanocrystal of copper, that really runs and runs. So the molecules still have to be stretched.
Now, there is, of course, the advantage of using some kind of heterogeneous electrocatalysts using organic materials. And the advantage is very clear, as I showed you in the very beginning. You know, you can manipulate the system, you can hook the systems or chemistry of organic substances is, of course, let's say, scientifically and maybe also industrially, a great edge on this story. So I know that there are, of course, inorganic. Chemie makes beautiful beautiful catalysts, homogeneous and heterogeneous, based on metals and nanoparticles, alloys, oxides. So all these things will play probably a role in future. But let's say from my background point of view, I was always focusing in this semiconductor, organic semiconductor type of systems, which definitely doesn't discard, let's say, Wolfram oxide in one point, or, for example, copper catalysts on the other side. There are very nice work also going on this nano-structured systems. But we didn't enter that field yet, and probably I will also be a little bit reluctant to go to inorganic metal electrodes. But there is a connection, if I may just add this. There is some kind of nanoparticle of metals immobilized onto polymer electrodes. I have seen that too. We didn't do work on that, but instead of this laying catalyst, for example, nano copper is somehow with ligands hooked onto the polymer electrode. So these kinds of hybrid, organic, inorganic hybrid systems might be the future. We will see. I mean, I'm very curious what comes out in the next days.
I don't know whether you remember, Michael, many years ago we had a discussion about photosynthesis, how to produce the fuels artificially. And there's a big field now, few generations. And at the time we talked about if we have a very efficient solar cells, silicon, and then use the silicon solar cells to do water spreading, electrolysis, and compared to use direct generation using catalysis and so on. And I don't know where the field stand at this point. And my belief is that it's still more efficient just using a conventional solar cells and do electrolysis and produce whatever fuel that you like to produce as a source of energy. And you can store it, you can do anything you want. So I know you're both involved in the solar fuels. And what is your perspective at this point of time?
Well, both, if I may answer first, both systems are viable. And so the disadvantage of the solar cell combination, I mean, it's a trivial thing.
Right, very trivial.
We have published also in this field with the perovskites using those as voltage source. But the issue is you first have to collect electrons, and then that comes at a price. Okay?
Ultimately, it's efficiency. Right?
Well, wait a minute. The others are not so bad. They're picking up. Okay, the direct. For example, cobalt oxide is high, 10% now, CO2 reduction. Cobalt oxide is a P-type semiconductor, and so it's. I think the verdict is not. The jury is still out, but it's certainly a competitor.
So I'm pretty sure that we had this discussion more than 10 years ago, and jury is still out. So maybe we can get together 10 years later and we talk about it again.
Yeah.
What about you?
I mean, my answer is here. I mean, this is definitely correct. This company, I mean, which we created under the name Solar Fuel, of course, helped us to make science in our field, but in the end of the day, to make money now, they went exactly what you said. For example, we have here these megawatt electrolyzers. So these are huge alkaline-based electrolyzers you can buy today. And wind energy now in Germany, but original idea is to get solar power plant, as let's say 10 megawatt plant, and you put this behind the solar power. If there is an excess of solar energy, you immediately turn them on and transfer it into the natural gas. And if the solar power efficiency is, let's say, on the order of 20%, these systems today are commercially available. You can buy this from this company, are on the order of 25, 27%. So this is not bad. 20% to 25%, maybe 30%, ends up in the end of the day around 6-7% overall industrial efficiency from light to chemistry, which is actually quite a good number in that scale, in the sense.
So this is very practical.
This is now commercial, let's say. But in the end of the day, if I could get this entire investment volume, let's say, into one power plant, like a solar power plant, which in the end doesn't give me electricity, but let's say a liquid coming out of the panel. Of course, the so-called capex investment, everything scaling with these are, of course, difficult technologies. You need a lot of platinum in these kinds of things. They are expensive. So probably it could be very competitive if we could do it directly. But you are right. I mean, if you want to do it today, this is the way how it's today available. But we are working as a scientist, of course, more in future than today.
But we can revisit this in another 10 years. Thank you very much for the lecture, audience.